My name is John Michael, and this is going to be my explanation for assignment 1. I'm going to go step by step each question. I'm going to explain everything that I did. So question 1, what are the dimensions of train images and labels and test images and labels? First thing first, as the assignment asked, we first need to import CARES datasets. Oh, sorry, we need to import fashion minutes from CARES datasets. So once we've done that, we actually made each test and train equal to the fashion minutes and load the data. Now, in order to see what the dimensions are, we print it as dot shape, and printing it as dot shape allows us to see what the dimensions of each individual is. Question 2, what are the lengths of train label and test label? Dot size actually allows us to see that, and because of that, we can see that train label is 60,000 and test is 10,000. Question 3, please show some train and test labels. Simply print it, and this is what it displays. Question 4, please show the digital content of image index 5 in the training dataset. So the digital content of the image itself is this. And we did this by doing train image and then calling the index 5 like this. Question 5, please plot the image of the index 5 in the training dataset. First of all, we need to first import matplot as PLT. Next, we save the train images into a variable called images. After that, once we have both things done, we do plot.imshow images and cmap equals plot.cm binary. Once we've done all three of that, we show the image and this is what's displays. Question 6, what is the label for the index 5 in the train level? So it's actually 2. Question 7, same thing as question 4, but this time it wants index 500. So we did that and this is what it looks like. This is digital content. Question 8, plot the image of 5. Same thing. There's no reason for us to import because we've already imported on top. So same thing, call the variable, or sorry, save it in the variable and then plot it and then show it. And then once we showed it, this is actually what the image looks like. Question 9, what is the label for 500? Actually, same thing, it's 2. Question 10, please import the models and layers from Keras library. So we've done that, right? We've imported both. Next, define the sequential mode and call it my network. So we saved the variable as my network and made it equal models.sequential. Question 12, reshape the image from 28 by 28 to one column with 784 neurons flattening using two methods, the video method and the book method. Video method is this. We import TensorFlow as TF, save the minist as minist variable, and then load the data. Once we've done that, we make model to equal the sequential mode, add the flattening, because that's what it asked, the neurons flattening, add the layer dense 128, layer dense 10. Now we compile it using the optimizer atom, and then we model.fit, and this is what we get. Book-wise, okay, the way we did in the book was actually save the train images into a variable, reshape it to 60,028 by 28, simple. Question 13, also please normalize the image by dividing the image by 255. First of all, book and video, we all save our methods in a variable called train images. Once we've done that, the video shows us to do it with using tf.keras.utils normalize, then train images axis equal 1. Bookwise, we actually make the variable a type float and then divide it by 255. Question 14, add one hidden layer that has 512 neurons using ReLU activation function. So first, we do have a variable called myNetwork. We add the layer dense 512, make the activation equal ReLU, and then input the shape as 28 by 28. Question 15, same thing, but this time 128 neurons using ReLU. So we added the same thing, layer dense 128. Question 16, somewhat the same thing, 10 neurons, but we're actually not gonna um, change the input shape. Um, Question 17. Use the following two settings for the compiler and run them separately and see what the differences are. First one is optimizer atom loss. Second one is optimizer RM sprawl. Okay, so the way we did atom is actually the same way we've done the rest of it, but the only thing we're changing is the compiler optimizer as atom. The arms prop is the same thing, and the only thing we're actually changing is the optimizer and the loss to categorical cross entropy. I forgot to say that, sorry. We also changed the loss for atom. Once we've done both of that, the difference is that optimizer atom is more efficient in large problem compiling. Unlike arms prop, it takes it step by step. Question 18. Now after the compilation, please try to find the pattern using the fit command. The epoch needs to be 10. Okay, so first of all, we're going to compile it as atom, sparse, the loss equals sparse categorical cross entropy, metrics accuracy. Then, when we've done that, really where the question is asking is in model.fit. So we do model.fit x train, y train, and as it stated, epoch needs to be 10, so we did epoch equals 10, and this is what displays. Lastly, question 19, how do you compare the fashion MNIST with what we learned in class using MNIST? Fashion MNIST has more neurons, making it more higher in the accuracy and of its fail loss rate. Unlike MNIST has very low neurons. And those are basically compared to fashion MNIST and MNIST, those are the differences. And yeah, this is my assignment one. Thank you.